All right, let's see how you did. There is no gravity in vacuum. That is false. And the vast majority of you said that. That's correct. That's good. Okay, vacuum just means there's no air. It's got nothing to do with gravity. NASA has built a zero gravity chamber. That is false. Now, I have to put a bit of a legal disclaimer on that. They have created an airplane known as the Vomit Comet that simulates zero G, but it's still happening in a gravitational field. So, bit of a, yeah. Gravity is the same as air pressure. False. Not related at all. Gravity pushes down. Mr. Bennett, how can it be false? Because it pulls down. Gravity is the same as magnetism. False. They sure seem like it, don't they? Gravity in space is zero. False. What do you think holds the moon in orbit around the Earth? It's not a big rubber band. It's gravity. What do you think holds the Earth in orbit around the Sun? Gravity. What do you think holds Pluto in orbit around the Sun? Gravity. Lots of gravity in space. During a full moon, the moon has a higher gravitational pull, creating a higher tide. Oh my goodness. Whew. What does a full moon mean?
That
like
Earth isn't covering.
It means, yeah, that the moon is, you can see all of it. You do realize that when there's only half a moon, it doesn't mean that half of the moon has disappeared, right? You do realize that, right? You just can't see it. Yes, I know. It's kind of like the little kid, you know, you can't see me, you can't see me. Peekaboo. Still here. Just because you can't see it doesn't mean it's not there. So, yeah, just because the moon is half doesn't mean that there's half the gravitational pull. The moon does cause the tides, but that's on a daily basis. Right? In fact, twice a day there's high tide. Twice a day there's low tide. Okay? So that is true. But yeah, a full moon, no. It has to do with actually how close the moon is to the Earth. That may be what you're thinking about. There are times when the moon is actually closer to the Earth, and then there is a higher tide. That is true. But it's not during a full moon. Okay? Yeah, the moon is still there when only half of it is, yeah. What weighs more? Oh my goodness. They're the same. Pound is a pound is a pound. Pound is actually a unit of weight. It's not a unit of mass. It's a unit of weight. Pound of feathers, pound of bricks would be the same. One would just be a whole lot bigger than the other, right? Black holes don't suck everything into them. They were all going to be false until I made this one negative where it says black holes don't suck everything into them, because that is, in fact, true. They do not suck everything into them. Have you been sucked into a black hole? I haven't. I'm something. Everything. Everything means everything.
I told Jason the answer is true, and then I wrote false for myself.
There are countless black holes out there. In fact, I actually read the other day that they discovered an exoplanet. Do you guys know what an exoplanet is?
Yeah.
Planet outside our solar system. It's only like about 20 million light years away, so not that far. It is actually entirely made of diamond.
We should get that plan.
Now, actually, that brings a whole new discussion. Something else I read about how diamonds, you know, that you have in your ring, really aren't that valuable and rare. The only reason they are is because the companies that are selling us to them are telling us that they're valuable and rare. They're really not that rare. And you know that, well, fair enough. You know that whole thing about guys should spend 20% of their salary on a diamond? You know why it's 20%? because they thought 30% they might not fall for it, the public. 10% they weren't making enough money, so they picked 20% and everybody fell for it. They're not that valuable, they're not that rare. Guys, do your homework. Girls, sorry. Which one of the following diagrams most closely resembles the gravitational forces that should be that the Earth and the Moon exert on each other? Note that the mass of the Earth is about 80 times that of the Moon. I'll let you guys think about that while I have a little. Okay, so which is the correct answer? The correct answer is C. What the heck is going on there, Mr. Bennett? Only 1 or 2 people got it right.
They're equal pull in there.
Zach is absolutely right. They have to be equal pull. If they weren't, what would happen? The moon would crash into the Earth, killing us all. Last I checked, we're still good. They must be equal. Don't you remember Newton's law that says what? Equal and opposite force. What does the equal and opposite force mean? It means equal. Right? So yeah, it can't be this one. It's got to be this one. Now, is this to scale? No, the Earth here should be 80 times bigger than the Moon, but that's obviously going to be very challenging to diagram. But the arrows are the important things there. Okay? Yeah. Equal. Opposite. That's okay. We are quite often start off with, is there one more? Or just 10? Yeah. Okay. All right. Not a problem, you guys. Don't worry about it.
Are we doing another one now?
Yeah, we're going to start another one. Now I'm going to do the free fall one.
Can I already
Probably not, no. If I have time at the end, I'll play a free fall and Tom Petty. Okay, let's talk about Galileo's famous demonstration. Anybody been to Pisa? No? Any Italy? Anybody in here that went to Italy with the travel club? No? Your sister did? Yeah, I think they went to Pisa. I'm not mistaken. I think they did. Okay, so free fall explained. Galileo showed that falling objects accelerate equally. Again, what does equally mean? The same rate, regardless of their masses. Now remember, Aristotle and his followers for almost 2,000 years believed that heavier objects would fall faster than lighter objects, but never got around to actually trying it out. Hard to believe. Yes.
Would people just notice that when we draw something?
You would think so. Yeah, I'm absolutely stunned every time I talk about this.
People probably knew, they just never realized.
Well, maybe no one was like the emperor has no clothes, right? Oh, Aristotle, he's Mr. Smarty Pants. We're not going to contradict him, but I don't know, kind of wrong. So yeah, this is strictly true if air resistance is negligible. Okay, in other words, if it's small enough that you can ignore it. That is if the objects are in free fall. It is approximately true when air resistance is very small compared with the mass of the falling object. For example, a 10-kilogram cannonball and a 1-kilogram stone dropped from an elevated position at the same time will fall together and strike the ground at practically the same time. Not 10 times earlier, which is what Aristotle predicted. This experiment, said to be done by Galileo from the Leaning Tower of Pisa, demolished the Aristotelian idea that an object that weighs 10 times as much as another should fall 10 times faster than the lighter object. Galileo's experiment and many others that showed the same result were convincing. But Galileo couldn't say why the accelerations were equal. Why are they equal? Anyone? Why are they equal?
The force on them is all the same.
Because the arrow.
He's almost right. Is the force the same? Keeping in mind that gravitational field is newtons per kilogram, right? So if you've got well, let's talk about these here, right? Like if you've got a 10-kilogram cannonball, and a 1-kilogram cannonball, the 10-kilogram cannonball is going to have how many newtons on it? 98 newtons per kilogram. It's going to have, 9.8. It's going to have 98, and the 1-kilogram one's going to have 9.8. So are the forces equal? No. Well, no, they're not. but the gravitational field is the same. What is the gravitational field? 9.8. I mean, it's important that you include the units. 9.8 newtons per kilogram. So why? How come? Bigger force should be bigger acceleration, Mr. Bennett. What's going on here?
They have a larger mass, you get a larger inertia, so the larger one has a little bit of a lag before gravity can take its land.
Well, sort of.
It says in the book.
Oh, yeah. Right? It might have 10 times as much force, but it's also got 10 times as much mass, which means it's not going to accelerate as much. In fact, the 10 times as much force, oddly enough, or conveniently enough, is exactly counterbalanced by the 10 times as much mass. And so they fall at the same rate, which is, in fact, 9.8 meters per second squared. That's the acceleration, right? Okay. So Galileo couldn't say why the accelerations were equal. Fortunately, we can now. The explanation is a straightforward application of Newton's second law and is the topic of the cartoon Backyard Physics. Let's treat it separately here. Let's flip the page over and read the cartoon. And you remember these cartoons aren't that much fun, are they? No, they're not. What's on the next page here of mine? If I drop the bag of clothespins and the single pin at the same time, which will fall to the ground first? Says the mama. And the one kid says, that's easy. The bag of clothespins is heavier, which means gravity pulls on it with more force. Is he right so far? Is the clothespins heavier? Yeah. Will gravity pull on it more? Yeah. So the bag of pins will accelerate more and hit the ground first. The other guy thinks, scratches his head. Not true. The bag of clothespins has more mass, which is to say has more inertia. Which is to say it will be less responsive to gravity and lag behind the single pin. So the single pin will hit the ground first. Sorry, they land at the same time. And the key here is that bottom one here, at the bottom here, if I can scroll down a bit. Let's see if I can see it here. Yeah. Okay. So the weight of the clothespins, big weight, signified by big word weight, over big mass, it's the same ratio. Small weight or small weight, small mass. What's the value of G? 9.8. Whatever the weight is in newtons divided by the mass, and whatever the weight is in newtons divided by the mass, doesn't matter how big it is, every time you divide it, it will always be 9.8. And that is the acceleration. Okay? Go back to the front page. And it's re-explaining it back on the front page as well. Okay? So recall that mass, the quantity of matter, and weight, the force due to gravity, are proportional. A 2 kilogram bag of nails weighs twice as much as a 1 kilogram bag of nails. So a 10 kilogram cannonball experiences 10 times as much gravitational force or weight as a 1 kilogram stone. The followers of Aristotle believed that the cannonball should accelerate at a rate 10 times that of the stone, because they considered only the cannonball's 10 times greater weight. However, Newton's second law tells us to consider the mass as well. A little thought will show that 10 times as much force acting on 10 times as much mass produces the same acceleration as the smaller force acting on the smaller mass. In symbolic notation, and they've got it there, they show little f over little m is going to be equivalent to big F over big M. And the big F is always going to be 10 times or whatever times bigger than the little f, and the big M is always going to be exactly the same number of times bigger, and you're always going to equal 9.8. On Earth, of course. This is where F stands for the force acting on the cannonball, and M stands for the correspondingly large mass of the cannonball. The small f and m stand for the smaller weight and smaller mass of the stone. We see that the ratio of weight to mass is the same for those on any object. All freely falling objects undergo the same acceleration at the same place on Earth, because oddly enough, gravity actually changes as you move around the Earth. There are certain areas on Earth that are slightly more gravitational than others. It's kind of weird. And if you watch the video that Ryan posted to Schoology a few days ago, it actually talks about that. It talks about the sea level and stuff. We can show the same result with numerical values. The weight of a 1 kilogram stone is 9.8 at the Earth's surface, and the weight of a 10 kilogram cannonball is 98 newtons. I sort of have it up there. The force acting on a falling object is the force due to gravity, or the object's weight. Using Newton's second law, the acceleration of the stone is 9.8 over 1, which is 9.8, or 98 over 10, which is 9.8. In the famous coin and feather in a vacuum tube demonstration discussed in Chapter 2, which we didn't see, The reason for equal accelerations was not discussed. Now we know that both freely falling objects fall with the same acceleration because the net force on each object is only its weight. And the ratio of weight to mass is the same for both. And there's a question at the bottom there, and I think, if I'm not mistaken, here's a question for you. Oh, you didn't even do it! Oh, don't look! I did I not? Oh. Okay, go ahead and try now. Oh, for crying out loud. I'm gonna have to show you that. Okay, correct answer is. Says you've all got it.
Go to the third one.
Oh. I'll see if it's on YouTube now. Now can I do it? There's the answer down there. Can you see it? Oh, I gotta get through all this stuff. Okay, so, oh yeah, we're going to get past the ad here from Visa. Thank you very much, Visa. So, actually, the question is, if you were on the moon and dropped a hammer and a feather from the same elevation at the same time, would they strike the surface of the moon at the same instant? Because what would happen on Earth? Clearly the feather would hit, or the hammer would hit the ground first, would it not? Yeah. Like, we know that. Even though I've already said, well, things hit the ground at the same time. How come we know that with a hammer and feather, it's like, how come we know that hammer's going to hit first? It's got to do with surface area, and it's got to do with air resistance and all that stuff, right? And that's because of our atmosphere. However, if you were on the moon, what would happen? Well, they actually tried it. They actually tried it.
I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather from our falcon. And I'll drop the two of them here, and hopefully They'll hit the ground at the same time. How about that? Mr. Galileo was correct.
Mr. Galileo, I always like that part. Oh, okay. Yeah.
That can't be right, there's no sound in space.
Excellent point, Jay. It's actually an electronic recording, right? With the microphone inside his helmet, so yeah. Yeah. So the correct answer is for A, it would be, for number 1 would be yes, they would land at the same instant. It has to do with air resistance. Okay? And I should really read the backside here. I don't know if I'm going to have time to go through all this. I'll try to read through it quick. The feather and coin fall with equal acceleration in a vacuum, but quite unequally in the presence of air. When air is let into the glass tube and again inverted and held upright, the coin falls quickly while the feather flutters to the bottom. Air resistance diminishes the net force acting on the objects. The net force decreases a tiny bit for the coin and a lot for the feather. The downward acceleration for the feather is very brief because air resistance builds up quickly and counteracts its tiny weight. We're going to talk more about this in the future, but it reaches terminal velocity very quick. Okay? The feather does not have to fall very long or very fast for this to happen. When the air resistance of the feather equals the weight of the feather, the net force is 0 and no further acceleration occurs. Acceleration terminates. The feather has reached its terminal speed. If we're conservative direction, which is down for falling object, we say the feather has reached its terminal velocity. Air resistance does not have as much effect on the coin. At slow speeds, the force of air resistance is very small compared with the weight of the coin, and its acceleration is only slightly less than the acceleration of free fall, or g. The coin might have to fall for several seconds before its speed is great enough for air resistance to equal and cancel its weight. Its speed at this point, perhaps as much as 200 kilometers an hour, would no longer increase, and the coin reaches its terminal speed. Okay, so when you do go to the Empire State Building and you throw the penny off, and you are hoping to kill someone on the sidewalk, is that going to happen? And the answer is it's not. Mythbusters, and I'll show you the video sometime, remind me, okay? The answer is it's not, because the coin will eventually reach terminal velocity. It won't continue to accelerate. The feather reaches terminal velocity quite quickly because of its large surface area and low mass. Okay? I'll explain that a little bit more in a bit. The terminal speed for a skydiver varies from about 150 to 200 kilometers an hour, depending on the weight and the orientation of the body. A heavier person will attain a greater terminal speed than a lighter person. The reason the greater weight is more effective in plowing through the air. Body orientation also makes a difference. More air is encountered when the body is spread out, and the surface area is increased, like that of a flying squirrel. Terminal speed can be controlled by variations in body orientation. A heavy skydiver and a light skydiver can remain in close proximity to each other if the heavy person spreads out like a flying squirrel, while the light person falls head or feet first. A parachute greatly increases air resistance and cuts the terminal speed down to about 15 to 25 kilometers an hour, slow enough for a safe landing. If you hold a baseball and tennis ball at arm's length and release them at the same time, you'll see them strike the floor at the same time. But if you drop them from the top of a building, you will notice that the heavier baseball strikes the ground first. That is true. This is due to the buildup of air resistance at higher speeds, like the parachutist in the question. At low speeds, air resistance is often negligible, but at high speeds, it can make quite a difference. The faster you go, the greater the air resistance. The effect of air resistance is more pronounced on the lighter tennis ball than that of the heavier baseball. So the acceleration of the fall is less for the tennis ball. The tennis ball behaves more like a parachute than the baseball does. When Galileo reportedly dropped the objects of different weights from the Leaning Tower of Pisa, the heavier object did get to the ground first. What? However, the time difference was only a split second rather than the pronounced time difference expected by the followers of Aristotle. They expected 10 times bigger, 10 times slower. If Aristotle had gone off not the Tower of Pisa, if he'd not just gone up a couple steps, would you notice any difference at all? None. The higher you go, the greater the difference. But it has to do with air resistance. The behavior of falling objects was never really understood until Newton announced his second law of motion. Isaac Newton truly changed our way of seeing the world. Okay, quickly. Backside here, cool little demonstration. If you drop a sheet of paper and a book side by side, what will happen? The book will fall first, right? Let me grab a book here. We'll start with physics. I love this because it always annoys Mr. DeRoche downstairs. Okay, piece of paper, book. Clearly one is probably about 100 times heavier than the other one. When I drop them, clearly the book landed first. Why? And they're even about the same size in air resistance, are they not? Okay? But this one can plow through the air, this one cannot. This one reaches terminal velocity about, now, this one reaches terminal velocity of the book, much higher, right? Okay, now what if I take two pieces of paper and do this? Two identical pieces of paper. Exactly the same weight. One crunched up, one not. Well, that absolutely a low. Smaller surface area. Okay, brightness. Let's take. The only reason I'm doing this is just so that it hides behind the book. What will happen when I've got the piece of paper on top?
They'll stay together.
Will the paper fall with the book?
Yes.
Or will the book fall and the paper will flutter to the bottom, just like this? Yeah, I know, I love doing that.
They'll stay together.
All right, who thinks they're going to stay together? Who thinks they're going to fall apart?
Because they're
Okay. You think because of the fold it might fall apart?
I knew it.
It creates the back.
Yeah, it creates vacuum, there's no air resistance. Now, what if I put the book like this going? Will the air resistance of the paper hold the book up? Will the whole thing flutter like this? Wouldn't that be cool? It's just a competition. Mr. George says, you're doing that thing with the book again, aren't you? Although it's Mr. Hugginson below me now. You can have to. Okay, so that's kind of neat. Quickly, these answers here. If a heavy person and a light person open their parachutes together at the same altitude and each wears the same size parachute, who will reach the ground first? The heavier person will reach the ground first. Like a feather, the light person reaches terminal speed sooner, while the heavy person continues to accelerate until a greater terminal speed is reached. The heavy person moves ahead of the light person, and the separation continues to increase as they descend, both at constant speed, but one just traveling faster than the other. So that difference will grow. Different terminal velocities. If the force of air resistance is the same for a falling baseball and a falling tennis ball, which will have the greater acceleration? Don't say the same. It's true that the air resistance may be the same for each, but that doesn't mean the net force is the same for each, or that the ratio of net force to mass is the same for each. The heavier baseball has the greater net force and greater net force per mass, just as the heavier parachute is previously considered. This is hard stuff, by the way. Convince yourself of this by considering the upper limit of air resistance, that is, when air resistance is equal to the weight of the tennis ball. What would the tennis ball's acceleration be? It would be 0. But when the amount of air resistance acts on the heavier baseball, do you see that the baseball still accelerates? And this is, again, I'm going to have to go through this again with you. The more thought, do you see that the baseball has the greater acceleration even when the air resistance is less than the weight of the tennis ball? So, I mean, the whole thing boils down to this, right? The acceleration is the same, but air resistance plays such a huge role, especially at either low speeds or high altitude. Because when you got high altitude, you've got a greater amount of time, and that speed difference will sort of spread. Okay, so there you go. Gravity.
Objects have the same length, just different shape.
Not